So, okay, now let us start. First and foremost, so I was talking about we will be doing today annealing and hot working, right? So, while discussing about this particular section, okay, I must actually, when I am using the term hot working, before that, we must actually understand one thing, which already we have a clear idea about it, but still, uh, like if I deform a particular material, if I deform a particular material, certain things are going to happen, and these things will happen because of the deformation. Like you can say, you can straight away say that after deformation, the strength of the material is going to increase. Okay, the strength is going to increase. Certain changes I am actually listing down here that we encounter after the deformation. Like one of the change that we encounter is that yes, the strength has increased. Sometimes the hardness also increases. But you see, everything comes with a price. So if I am talking about that strength increases, hardness increases, at the same time, another disadvantage that we have is along with the increase with the percentage deformation, as we increase the deformation percentage more and more, along with the increase in the strength and the hardness, what happens is the ductility of the material decreases. Ductility means that how much elongation, how much the material we can actually duct. Ductility means what? Ductility means, say for example, practically I am trying to make you understand. So I have actually taken a specimen. Now if I say that this specimen is actually ductile, what it means is that I can load this specimen and I can deform it substantially. So it is going to change the shape of the specimen, but the specimen is not going to break. So obviously, with more and more elongation, there is going to be reduction in the area, okay, of this specimen. That is why here we have shown the specimen to be elongated and thin, something like that, because there has been substantial reduction in the area of the specimen. But if the specimen is ductile, then without failing or without fracturing, I can actually elongate the specimen quite a lot, right? And we know that ductility depends upon a lot of things, and one of the very important characteristic, one of the very important means thing on which the ductility depends is the crystal structure. ये crystal structure के ऊपर भी depend करता है. That is why aluminium, copper, they are actually ductile. Because why they are ductile? Because they are basically FCC. Now, if I try to deep dive into this also, like say for example, I have said that aluminum and copper, they are actually ductile. Now, after that, my statement was they are ductile and most of the FCC metals are ductile. So I can say that aluminum and copper are ductile because they are FCC. Now, when I'm talking about the crystal structure, then again, if I try to understand that why this kind of thing is actually taking place, we have to get into the dislocation theory. We have to get into the dislocation theory. I know that from our dislocation classes, I think it is clear, all of you can answer now, that FCC crystals, they are having quite a great number of slip systems. So they have, FCC crystals have active slip planes. Many active slip planes are there. So because they are having active slip planes, and basically FCC having 12 slip systems, we know that. Now what happens is, and as the slip planes are very, very active, the slip is very common. So the dislocations, they can move very easily in case of FCC materials, and or we can say in case of FCC crystals. And as the dislocations, they can really move very, very easily. Okay, that is what it is making the material easily deformable. Because the dislocations are moving easily, the dislocations are gliding easily, so the material is becoming deformable, easily deformable. So it is making the material ductile as well. But okay, our point was that as we are actually increasing, as we are actually deforming a particular material, now with the deformation, what happens? The strength of the material is increased and the hardness of the material is increased, but with the cost of decrease in the ductility. This is a general, what should I say, observation that is being observed. Now, first and foremost, let us understand one thing. Let us understand what is cold working. What is meant by cold working? Now, if you talk about cold working, okay, we need to say that, see, cold working means what? Cold here doesn't mean that we are not talking about the freezing point or something like that. Cold working here means we are more specific about the temperature where we are, at which we are actually deforming a particular material. So the temperature should be, it is not very high. So the temperature, and also it is not the room temperature also. We are not talking about the room temperature deformation. Sometimes cold working means, obviously, that is the room temperature deformation. But generally, when we talk about cold working, the temperature that we talk about, it is variable. It depends upon the temperature, the melting temperature of the material. And it is 0.3 of the melting temperature of the material. That is the exact temperature that we say. For example, I take an example. If suppose we know that steel, I am talking about steel. Say suppose the melting temperature of the steel is, we know what is the melting temperature, we can say 1500 roughly. So if 1500 degrees Celsius is the melting temperature of steel, so if I am talking about 0.3, that means 3. So the cold working temperature is going to be around 450. So for steel, if I am having, if I am maintaining the temperature to be 450 degrees Celsius or 500 degrees Celsius, and I am actually, working, I mean, I am deforming steel, then for steel, it is actually what? It is the cold working. But my question is, will this temperature be the cold working temperature for aluminium? Shruti, will this be the cold working temperature for aluminium? 500 degrees Celsius? Tell me. Like,
No, sir. Right.
okay. So why you say that?
So because aluminum's like melting temperature is already low.
Yes. So aluminium, the melting temperature is how much? So whatever it is, say for example, uh, the melting temperature of aluminium we are taken. Uh, so aluminium melting point, it is actually 660 something like that. So yes, if it is 660, then I can say that it is about so 3 by 10 into 660. So this is going to be the melting temperature. So around 200 degrees Celsius. Sorry, not the melting, the cold working temperature for aluminium. So you see, this is actually variable. It varies. A temperature, cold working temperature, which is appropriate for steel, that may not be appropriate for all the materials. So if I kind of, if we say that what is cold working temperature, then what is cold working rather? So the definition, and don't bother, actually the notes also you will get. Okay. So when a crystalline material, okay, is plastically deformed, when a crystalline material is plastically deformed below about 0.3 of the melting temperature. Okay, it is called the Tm stands for TMP is the melting point or the melting temperature. So it is called, we can say, cold working. Now, sorry, what happens with cold working? Cold working means nothing but plastic deformation, like we have already said. When I'm talking about cold working, what it means is the plastic deformation. So plastic deformation of a material, and when it is when I am actually deforming it at a lower temperature. So in the process, what we are actually doing is in the process we are doing certain things. When I am deforming it, a material at a lower temperature, substantially, then I am doing certain things. And what are those things that actually we are doing? Number one, we are increasing the dislocation density of the material because plastic deformation is taking place. So one very important thing that we encountered is the plastic deformation. And with the plastic, why the plastic deformation is taking place? That is because of the slip by the dislocation. So I can say the plastic deformation by slip. Okay, by slip. So slip of dislocations. So dislocations, they start to move. Dislocations, they basically start to move. They move right on preferred slip planes. On preferred slip planes, right? And this increases because of this plastic deformation. This what it does is that the dislocation density drastically increases. I can say dislocation density, which is rho, I call it rho, we call it rho, it increases drastically during cold working. Okay. Now, see here, when I'm talking about the dislocation density and I'm talking about that it increases drastically during cold working, we need to understand one thing that what is the range? We need to understand because sometimes direct questions also come in the gate, also it has come. They have asked about the range. Say, for example, if we are talking about an annealed material, annealed means you, I think all of you understand that it is a stress-free material, right? We have heated the material, you know, at a means subsequently high temperature, and we have substantially heated it for quite a long period of time, and then we have cooled it. Okay, that is called annealing. So in heat treatment, again, we'll see all these things. Heat treatment will also have to cover anyway. So if I'm talking about the annealing portion, in case of annealed material, you see the density, the dislocation density, it is about 10 to the power 6 to 10 to the power 8 per meter square. So you see, here also I need to, I mean, tell you one thing. Here the unit, just look at the unit. What is the unit that actually we are using? So in case of dislocation density, if I am talking about dislocation density, you can encounter two kinds of units. One is meter per meter cube. Another is sometimes they just simply write meters per meter square. That is per meter square, something like this. So what it means is that uh, if I am talking about, say for example, the C is the same thing. Okay, one and the same thing, and both are correct. But in case of dislocation density, we encounter this unit mostly in all the standard books in Dieter, and if you go for Dieter, Hosford, or books like Courtney, okay, there you will see this unit only per meter square. Okay, but by definition, both the units are actually the actually correct. Why? Because I tell you now why. What this is actually saying, meter per meter cube. Okay, let us then look at, I mean, just explain this portion a little bit. If I'm talking about the rho, that is the dislocation density. Okay. And if I'm talking about the unit of the dislocation density, we are talking about. And now meter per meter cube, if I am talking about this unit, what it means is that, it means that what is the length, total length. Suppose I have got, we are actually considering a volume, one volume of a crystal. So unit volume of a crystal, entire crystal I have taken, something like this. So you see, understanding these basics are very, very important. That is what is going to make you people strong in metallurgy from rest of the people, I mean, from the crowd. So this is, suppose this is a crystal, okay, and I'm considering unit volume of this crystal. So that means that, suppose this is the 1 meter, this is 1 meter. Say for example, I am actually taking a cube of this shape, and this is a crystal. Now we are calculating, now in this crystal there will be many dislocations. You can understand. So one dislocation can be like this, another, these are defects, right? Dislocations are nothing but defects. So these are all the dislocations lines, the defect lines that we are actually having. Getting my point? So these are the defect lines that we have, right? So what I will do now is that, according to the definition, we are going to add up the lengths of all these dislocations. Say for example, if this is 1, this is 2, this is 3. Now obviously this is not possible. You can very well understand that this is a conceptual theory that actually we are understanding, we are trying to get into. So we will actually count all the dislocations that are there in the unit volume of the crystal, and we will add up the length of all these dislocations, and that is going to come up in the numerator, the total length of the dislocation. So summation of the total length of all the dislocations that are there in the unit volume of the crystal, so divided by the volume of the crystal. So in this case, the volume of the crystal already we have taken as unity. That is the unit volume only we have considered, 1 meter into 1 meter into 1 meter. So that is the meter cube is, that is why the meter cube term is actually coming at the denominator and the meter term is actually coming at the numerator. Okay. Now, okay, another term that we encounter is that the unit of the crystal is, that is 1 by meter square, something like this. Now, what it means, that is per meter square. It means that when we consider a 2D, this is a 3D picture we have considered. This is the volume. Sometimes, in most of the cases, what we will consider is, basically, we will consider grains, okay, two-dimensional grains or things like that. So there we will be considering the area, area of the grain, or area of the whatever you call the crystal. So I can take the area of the grain, okay. So in the denominator we are considering the area of the grain. Suppose in this grain, okay, how many dislocations are actually there, we are going to count that. So in 1 unit area of the grain, my number of dislocations, so that is going to actually give me this unit. So both are, and by this also you are actually getting what, meter by meter cube, we are actually coming to 1 by meter square only. So both these units, the point is both are actually correct, but per meter square is more frequently used, okay. So you see, when I'm talking about the annealed part, uh, then what happens is, it is 10 to the power 6 to 10 to the power 8 per meter square. That is the dislocation density rho for the annealed. And when we cold work a particular material, that is after cold working, what happens is, this rho value, it increases substantially, and it becomes 10 to the power 12 to 10 to the power 15 per meter square. Okay, so you can actually see that how my dislocation density is actually increasing. Okay, it is increasing so much. Okay, now you people will tell me, we have had enough discussion about the thing is about our dislocation theory. Now you tell me that what is going to happen during cold working as my dislocation density is increasing. Now what are the effects? What effects that actually we can expect? What effects we can expect? Shruti, tell me what effects we can expect because of rise in the dislocation density. Shruti, are you there?
Yes, sir.
Yes. So what effects we can expect? Means what the dislocations will do. We have seen that uh, with plastic deformation. I have said that in case
The
of any
mobility of the dislocations decrease.
mobile, okay. So you say the mobility of the dislocations decrease, and why is that? Okay. Now the Subhrajyoti can tell me why. Subhrajyoti, Suti is saying that with the rise in the dislocation density, the mobility of the dislocations are going to decrease. Why? Why something like that?
So the density is increasing a lot.
Okay.
So that means that the dislocations will interact with themselves. Now the when the interaction is between the same signed ones, like a positive edge dislocation is interacting with a positive one, so they will repel each other. While
Mm.
the negative, I mean, the opposite sign ones will interact. What will happen that they
Yes.
will annihilate each other. So,
Okay.
due to the interaction of the same signed ones, the interaction
Mm.
will be hampered.
Okay. But yes, you are absolutely correct. But when you talk about the positive and the negative and things like that, then maybe you are just considering only the edge dislocations. Okay. Right. Shubhrajyoti, you considered only
Yes,
about
sir.
edge
Uh,
dislocations. Then
yes,
only
sir.
we will talk that some
Screw. Hmm,
dislocation is, yes, someone is positive and someone is
hmm.
negative. Something like this. So you considered something like this. Yes, it's true. But see, most importantly, yes, you are absolutely correct. But the main thing is here that you should be saying that dislocations interact, and through the dislocations interaction what happens is we have seen, you know, a lot of phenomena. Say for example, kinks can be produced. Okay, jocks can be produced. We have seen all this, right? Kinks and jocks. Now kink, you see, kink is actually what? Kink means the kink, when kinks are produced, you see, when kinks are produced, what happens is uh, we can say that this actually gives rise to glacial dislocations only. Glacial means the kinks can move because the kinks are in the same plane. Okay, but the jocks, you see, when the jocks are being produced, now the jocks means it is the jock part, that the a dislocation is going out of the plane, out of the slip plane, original slip plane. Now this will actually create a hindrance to the movement of the dislocation. Okay, and anyway, kinks also is a hindrance, but maybe with more stress, the kinks can move, but the jocks cannot move. Okay, see, kinks and jocks, these are the results of the dislocation interactions. Apart from that, dislocation tangles. Dislocation tangles means what? We actually uh, talked about, in case of, if you remember, in case of FCC metals, we talked about frank partial dislocations. You remember uh, frank partial? So what happens in case of frank partial is, suppose there is a dislocation B1, but of Barger's vector B1, there is another dislocation of Barger's vector B2, and these two are actually moving along in two different planes. Okay, One is suppose this plane and another is suppose this plane. So B1 is moving in this plane and B2